All right, I'll go through this. I'm sorry I didn't copy this for you, but it's probably okay. Let's talk about explosions and momentum. So up to now we've been talking about an object hitting another object, but what if there's just something at rest and it breaks into pieces, which is sort of the definition of momentum, right? Or definition of an explosion.
Where are you reading this?
You're not. I don't have it for you.
Oh.
Common examples of the conservation of momentum center around two or more objects colliding in the absence of external forces. Another twist on the example of a collision would be the idea of a reverse collision or an explosion. If you videotape an explosion and play it backwards, it looks like a collision. Likewise, if you videotape a collision and play it forwards, it resembles an explosion. So they are one and the same, just sort of opposite directions, I guess. If we look at the case of a cannon being fired, we find there's a force in the gunpowder exploding, creating a force in the cannon pushing on the cannonball, and the cannonball pushing back on the gun. These two forces are equal in size but opposite direction. If any forces that are external to the cannonball system, such as weight and friction, are removed, then momentum must be conserved. In the example here at the left, now what does this thing here right mean? What does that mean, that funny looking thing with the P?
It's a Greek symbol.
It is a Greek symbol, Mike. You know what Greek symbol it is? No, it's the Greek letter, I think it's an S. That's a capital sigma. And in statistics, it means the sum. The sum of all the momentum. Okay, so that's sigma P, sigma momentum. Sum of all the momentum. So at the example on the left, the external forces have been removed by placing the cannon on a frictionless surface. In the beginning, both the cannon and the ball are at rest. As a result, the total momentum before the collision or the explosion is zero. Since the total momentum of an isolated system means there's no external forces conserved, then the total momentum after the explosion would also be zero. Once again, Pi equals Pf. The only difference here is that the initial momentum is a big fat zero. Mathematically, they make it way more confusing than it needs to be. Let's just have a look at this here, because eventually you're going to see some crazy physics prof explaining this to you, so let me do it in regular guy language. Sigma P is equal to sigma P prime. What the heck does that mean? It means the sum of all the momentum before must equal the sum of the momentum after. So we've got momentum of cannon plus momentum of ball is equal to momentum of cannon plus ball after. But all of this has velocity of zero, so the momentum before is a big fat zero. And then you'll notice here that these guys, one's minus 200, the other's plus 200, and momentum is conserved. You will notice that the cannon has a new velocity that is in the opposite direction of the velocity of the cannonball. Remember, momentum is conserved, not velocity. So the mass of the cannonball is 20 times smaller than the mass of the cannon. As a result, the velocity of the cannonball is 20 times larger. 40 compared to 2. Consider what would happen if you had a cannon with a small mass and a ball with a large mass. This concept of momentum being conserved in an explosion is true for an explosion along a line, one-dimensional, as in animation with the cannon at the start, an explosion along a plane in 2D, or an explosion in free space, something like a hand grenade. When a hand grenade explodes and there's like 100 pieces, if you could take all those 3D vectors and add them all together, you would end up with, if it was at rest. What if the can or the grenade is being fired and it's traveling at some speed? Well, yeah, when it explodes, right, you've got all these pieces, but they're going to have to not add up to zero, they're going to have to add up to that. That's a really poor example. Let's try that again. Right, all those little pieces have to add up to that one, right? They would actually, you'd have, can I pull this apart? No, I can't. Anyways, it would be like this, right? It would be like that. All those pieces would have to add up to that initial one. We'll get into those. Okay, let's go straight to those examples, shall we? One's got a firecracker, one's got a Mr. Potato Head. Everybody loves Mr. Potato Head. He makes physics fun.
I like the replace that.
Yeah? A firecracker is sitting on a tabletop and explodes into two pieces that are 100 grams and 200 grams. After the explosion, the first piece moves to the left at minus 1.2. How fast does the second piece move? So we've made it simple by turning it into a single one-dimension thing. So let's just say Pi is equal to Pf, which would be the same thing as sigma P is equal to sigma P prime. What did he say? Yeah, you know, when we were in LA at Christmas time, we went to Universal Studios, and they had a guy in an Optimus Prime suit walking around. It was really cool. He was yelling at people, scaring little children. Hey?
Yeah, the real
He did, yes. It was awesome. He's about like 8 feet tall too. I don't know how he did it. It was like you know those big things in Avatar? It was like that kind of thing on a smaller scale. It was pretty cool.
What was he yelling? You remember?
I don't know. The guy was wearing like a basketball jersey, number 53, and he was like, number 53, you will, perish today. He's just giving it to him, right? He goes like, then Bumblebee showed up. That was cool too. Turned into a car. No, I didn't. But there was a lot of chintzy guys like out on LA Boulevard with chintzy Bumblebee suits on. They looked pretty lame. They're like kids wearing their pajamas out there on the street and charge $1 to take a picture with them, kind of thing. How'd I get into that? Okay, so we got PI is equal to PF here, right? So what's the initial momentum equal to?
0.
0. Do I need to write anything over on the left?
Straight 0.
Just write 0, Matt. Make it easy.
Yeah.
Don't make it hard on yourself. Let's write M1 V1 plus M2 V2 there. If you want, you can put your primes, because technically that's true. The mass of one piece is 100.
Times 1 negative 1.2.
And it's going left at minus 1.2. And the mass of the next one is 200. And we're going to solve for V2 prime. I've really made this pretty simple for you, haven't I? Right, so I'm going to multiply and then take the left-hand side. So that's going to be minus 120. Take the other side, it's going to be 120. 200 V2 prime. V2 prime is 120 divided by 200. And I do not have the answer in front of me. 0.6?
It's 0.6.
Yeah, I think you're right.
I did the math in the calculator.
Which makes sense because it's twice as massive, so it's going to be going half as fast. That's really not that hard, is it?
Wait, it's twice as big, so it goes
Half as fast, right? Now, what would you do if the firecracker was already traveling at a certain speed?
We just don't know what to do.
You know what?
You just plug it in.
Flip the page over and let's do a question like that, because you might run into that. I feel like I can do it right now. Let's call this one 1A. Flip the page over, and I'll just write, suppose the initial firecracker was traveling at, I'll make it easy, 2 meters per second.
Then you just plug it into the left side like before, right? Two milliseconds.
Isn't that cool? How much software do you think, what programming went into that for Bartek, do you think, eh? More than Scratch, right? Yeah. Okay, so if it was initially traveling at 2 meters per second, what's the mass before?
300.
300, right? So let's
What?
write, because it's 2 pieces, Mike, right? 100 and 200. I'm going to write PI is equal to PF. So before I'm going to have I'm just going to write MV. Here I'm going to write M1 V1 prime plus M2 V2 prime. So now I'm going to have 300 times 2, or 600. And here, this is now my 100 times minus 1.2, and this is 200 times V2 prime. What's extra hard about this? Anything?
No, you just move it through the numbers.
Really nothing, right? I mean, all I've done is instead of having 0 on the left, I have a number. 0's a number. So now I'm going to have 720 is equal to
Equals 3.6. That's the V2 prime.
3.6 meters per second?
Yeah.
That seems reasonable.
720 divided by 200.
Why is it so much more to the right? It's already going right. In fact, what was the answer before? 0.6. Oh, I was kind of hoping it was going to be 2.6. Are you sure, Mike? 3.6?
720 divided by 200.
Yeah, okay. Yeah, you're right.
You don't have to subtract the velocity, because if it's moving 2 meters per second, then with 100, we multiply by 0.8 meters per second. So it's going 2 meters.
This one, the 100.
Yeah. So it's going 2 meters per second to the right.
No, but I'm given that the end result is minus 1.2, right? So why is this not 2.6? Well, because it had a lot of force. If it's now traveling to the left, and there was more force to the explosion to make it go from, instead of going 0 to 1.2, I'm going from 2 to minus 1.2. There's a greater force in the explosion, which is why the second velocity is so much more. Make sense? I wasn't sure I understood that until I explained it. Let's have a look at this potato head. A potato with a mass of... Do you guys want to try this one yourself? Why don't you try Mr. Potato Head yourself? Spend 5 minutes and I'll do it.
Yeah.
All right, let's have a look at Mr. Potato Head here. So the mass of the potato is 6. Slides with speed 4 across the frictional surface. The potato explodes into 2 pieces. Oh, this is like the question that I just did, isn't
Yeah,
it?
you do it the same way.
Exactly the same. Okay.
So you just do MV on the left side, nothing else.
Yeah.
All these
Does that sound okay? M1 V1 plus M2 V2. I guess the only thing that's different here is I didn't tell you the mass of the 2 pieces, but as Alex so aptly pointed out,
sarcastically
pointed out,
treating like a potato head.
the mass of the first one is 2, so the mass of the second one has to be 4. So this one is 8 V2 prime. So we got 24 is equal to 16 plus 4 V2 prime. 24 minus 16 I think is 8 equals 4 V2 prime. So V2 prime would be 2 meters per second.
So that means that they're all going...
They're both traveling in the same direction, one just faster than the other. Oddly enough. Could be, yeah. I don't know. Some sort of directionally explosion-enabled potato. Very interesting.
That's it.
All right, that is all, my friends.
Shaped records.